Yeah, and thanks for inviting me. It's been a great week so far. So you know the phrase peace through deterrence? It's a euphemism for the preparation for a global thermonuclear war. Anyway, the strategy here will be joy through deterrence. Okay. So, probably kidding. Okay. Going to start with some warm-up, which will be kind of sort of sociological. And then we'll kind of do some review and then some practical things. And that'll kind of continue into the second lecture. So I'm going to focus on dark matter models and not on testing dark matter. So apologies if you want to hear about testing. There are a lot of other talks on that here. So this will be about models. We have one number. That or so. So I'm going to let me just start by giving kind of a sociological categorization of different like dark matter model papers, sort of what are the goals of the authors maybe, or how would I categorize them. So let me say dark matter model goals. Right, there are a lot of models for dark matter, so let me just kind of put them in different categories. So of course, kind of most famously would be models that connect dark matter to another open problem. So we would call these kind of motivated. Or top-down. So of course, kind of classically, we have models that connect dark matter to the hierarchy problem, like the WIMP. Or we like models that connect dark matter to the strong CP problem, like the QCD axion. Or you can connect it to baryogenesis. One thing that I think is sort of understudied, but would be in this category, would be models that try to address why is this an order 1 number. Yeah, which I think is sort of an underappreciated puzzle. Even if, no matter what dark matter is, like the baryon energy density is proportional to the proton mass. From a UV perspective, that's exponentially sensitive to kind of UV threshold corrections to the strong coupling. So even if you kind of fix the dark matter abundance, you know, the baryon abundance could have been very different. So why is this ratio order 1? Yeah, I think there's been so almost everything I'm going to talk about in these lectures is not going to address that puzzle. So most models for dark matter don't address that. There's sort of 3 categories of solutions people have proposed I'm aware of: anthropics, like a really good Z2 parity, plus asymmetric dark matter, or maybe some sort of dynamical response to the baryon energy density, something like a relaxion. There's been kind of recent interesting work from the Maryland group studying some of that, but generally I think this is very understudied. So I'll just kind of say I think this is really worthy of more attention. But it could just be an accident, so I'll be mainly taking that point of view. Yeah.
So in this class of connecting to another problem, it's only ever solving 2 problems, right? Is there any models that would solve 3 problems?
There are models that try to solve n problems, yeah.
Oh, really? More than 2?
But usually 2. I mean, there are ones certainly that, yeah, would do these 2, but yeah, like a twin Higgs with an asymmetric dark matter, for instance, just an example. But yeah, typically 2. 2 is already really hard. Okay. Mainly, I'm going to be talking about 1 problem today.
There are like 2 new cosmological problems, like HNAP and SA.
Yeah, and also
try to do something with that.
Connecting to that is also interesting. Most of the things that address those 2 don't connect it actually. Like for HNAP, you kind of want some new percent level contribution to the energy density around recombination and what in the explicit models it's not connected to dark matter. But that's also worth thinking about, and I'm not going to discuss those problems anymore. Okay. So kind of a second category that is very popular is to consider models that explain an anomaly. The anomalies are time dependent, but there have been many, many models in that category, and some are really clever. In my opinion, the best ones are the ones that live after the anomaly died because they were a qualitatively new idea that highlighted new phenomenology. Kind of like a classic example would be like inelastic dark matter, which was proposed to address Dama. It doesn't really work so well for that anymore, but it's still like a very interesting possibility in the connection of that kind of leads to new phenomenology and direct detection. Okay. Okay, another category looking under the lamppost, or what I would call kind of portalology, which is to kind of think carefully about the different operators that might connect dark matter to the standard model and then study to death their phenomenology. So, for example, the kinetic mixing portal, right, the neutrino portal, the different Higgs portals, I call it, say, S. And of course, higher dimension operators you can also consider. Or dimension, whatever, dimension 6 operators. And then there's, of course, a lot. But especially these kind of marginal ones have been studied a lot because they are motivated to think about, of course. Okay, so this would be kind of looking under the lamppost. Hopefully it couples to us, so let's study the signatures that would result from the different couplings we can think about. Okay, sort of another category is what I would call sort of signal building, which would be to kind of highlight dynamics that dark matter could have that would lead to new experimental signals, but maybe not worry about the motivation. But if it kind of points to a new signal, then that's interesting. Kind of like an example in this category would be like boosted dark matter from Jesse and collaborators. I'll give you an archive number. And here the idea would be like there's some other particle that maybe is also around in the Milky Way that, say, annihilates into dark matter. So here I'll call dark matter chi. And then you have relativistic dark matter produced maybe at the center of the galaxy. You can look for that in indirect detection or direct detection. But this may or may not be connected to the actual production of dark matter or any other problem, but it could point to signatures that we would miss if we don't look for them. So some models are kind of adding structure that leads to new phenomenology. So, okay. Okay. And then kind of the final category that I'll mention would be kind of what I'm going to actually focus on in these lectures, which would be to kind of try to classify models based on how dark matter is produced. Maybe abstracting the Lagrangian and thinking more about the cosmological dynamics, and then trying to identify different categories, like thermal relic models, or like an example that I put in this category would be like the class of models called Friesen. So I'll review later what that is. And here it's kind of a broad idea which would have sort of many different Lagrangian realizations. And the idea is to kind of think about the cosmology and classify models based on the cosmological behavior, which can then inform the experimental signals. Any other categories that I should add here?
Let me ask about, are you always assuming that there's one dark matter candidate?
Yeah.
That gives you all the one, two?
Yeah, good question. And of course, there can be multiple contributors. Right, for the baryon energy density, there's a bunch besides just hydrogen. So for these lectures, just for simplicity, I'm going to assume one thing, and then everything I say you should sort of extend to the generalization that there could be multiple things. So, and that I think, yeah, like from this point of view, then any production mechanism could be contributing some component of dark matter that's less than the full amount. So we should certainly.
It was also, I don't know, I would say that it's not like conceptually different models. It's all like phenomenology of possible dark matter, approaches, right?
Mm-hmm.
So in this way, I mean, would be interesting to see like some favorites, right? That something which goes for certain kind of deep understanding of why we have this dark matter overall, right? I mean, kind of consistent model which would be a little bit of explanation for its existence. You see what I mean? That this classification it's kind of sorting out different approaches. Right?
Yeah.
No, it's okay, right? But
yeah, hopefully there's
something which is deeper than that, which is not dark but which is bright.
I hope so. But I'm gonna take the approach of classifying different possibilities for you, and then I'll leave as an exercise to the audience the D principle towards truth.
Yeah.
But indeed, well, like for number one, I mean that's one reason people probably originally people only considered models that were connected to another problem because we would think those are the most motivated models to consider, and some people will take the attitude you should only consider models in category one, and I think that's an attitude one can take, but then that would exclude considering a lot of models and signals that don't arise yet in that way. But these are different approaches. This is really sociological classification. These are all, of course, connected to each other. So one can, for any sort of mechanism, one can try to connect it to other problems. One can add portals to it and look at the signals. So in reality, this is just a sort of crude sociological classification. Yeah.
So where would you put CDA in this?
Perma black holes?
Yeah, like
The number 5, I think. Of course, then depending on the situation, there can be signals. So you could put it in 4 if you want. Yeah, 4 or 5. Say. Yeah. What other problem?
I guess I will speak a little bit for the post-inflationary people, right? But in trying to understand the consequences of post-inflationary activity. But I think also if you're trying to understand the origin of galactic black holes, that some people see primordial black holes as a solution to that problem.
Ah, okay.
Yeah.
Sure.
From an astrophysics.
Yeah, I think that's fair. Okay, yeah, not hierarchy of strong CP. Definitely it can be connected to inflation. Normally it's non-minimal models of inflation that would lead to it, and also astrophysical problems.
Given the large body of constraints we have, does it make sense to even talk about signal hiding models?
Sure, yeah. Actually, yeah, I want to, yeah, in a second. I'll give some examples of nightmare scenarios in a second, just because I think I should start with that. Okay. But yeah, indeed, it's very easy to think about hard to find models for dark matter. Okay. So I'm not going to talk much about phenomenology, but let me just kind of make a quick statement about dark matter mass. So if it's all of dark matter, then there's a minimum mass, which we call fuzzy, which would be sort of 10 to the minus 20-ish, where people kind of argue about whether the bound is minus 19 or minus 21, but that's sort of when the Rowley wavelength is the size of dwarf galaxies. And there's kind of an important boundary at about a keV. Heavier than a keV is where fermionic models live, just because you can't fit enough fermions into dwarfs if they're lighter than say hundreds of eV. And also, this is where fermions live, and also this is where sort of thermal thermal-ish models live, by which I mean that the different momentum modes are populated like an equilibrium phase space distribution or sort of any basically phase space distribution that's not everything at rest. Because then you run into warm bounds. It's just a parametric coincidence, but the warm bounds and the fermionic bound are both around a KEV, which makes it easy to remember, but that's actually an accident, parametric accident. But yeah, so fermionic models and thermal models live here, which means the models here are just bosonic and kind of classical in the sense you have high occupation number, and from the perspective of the production, everything is produced at zero momentum relative to, say, the temperature of the universe. Okay, good. So you asked about hiding, so let me just start by giving examples that are hidden. So people would maybe call the nightmare scenario the case where maybe we only couple to it gravitationally. All the evidence so far is gravitational. And it's kind of easy to think of examples. And you could just have, say, a scalar with a mass. This can be produced by the misalignment mechanism. When the Hubble is on the order of fine, this just relies on gravity. And it might have no interaction with this. So it's kind of boring, but simple. You could have, and I'll kind of review misalignment later, maybe. Dark matter could be primordial black holes. So also, kind of, you could think about primordial black holes that evaporate into dark matter. So I'm sure it's an older idea than this, but I'll just kind of highlight a paper in this category by Hooper and Gordon. And
then because of the loop, you will get interaction of a different kind, electroweak or whatever.
Yeah,
level, right?
At some level, but
very consistency to say that nothing else is there.
I agree. Yeah, so I mean, assuming this is the leading way it's produced, then everything else could be smaller than what we can probe now.
Yeah, but even if you do not have to estimate how big it is, right? Because it's not conversion.
Sure. Okay, yeah, and then maybe it does interact more, so and then we could put those interactions. And
okay,
yeah.
It goes to the gravity, but the gravity proves to be producing, some effect which is, of unknown magnitude, right?
Yeah. So by nightmare, I mean posit that those interactions are small. If those interactions are big, then we're good.
But in this nightmare scenario, then it would suggest then that there's no connection to the ratio of
Yeah.
matter to visible, right? Because if you're going to make a connection to that ratio, you would expect the dark matter maybe to have a coupling besides gravity.
Yeah, I agree. Although I guess in a Z2 type scenario, there may or may not be a coupling. If that scenario addresses hierarchy, there will be. But yeah.
But I guess in this scenario, if it's really nightmare, maybe then you're relying more on anthropic for the ratio.
Yeah, or as an accident. Yeah, but I agree. So that ratio, and indeed, and that's one reason I think it's understudied. Yeah, and that might be a motivation for dynamics. I agree completely with what you're saying. Or you could have, say, a completely secluded sector that reheats independently. So that it has its own thermal history that's distinct from ours. It might have a different temperature. If you write a specific explicit model, usually there'll be some interactions implied by the reheating. Like, for example, if the inflaton decays both to us and to them, then through the inflaton you do couple to it, but those couplings can be very small. So in principle, you can independently reheat with very small couplings. And then you could, well, just for example, it could just be a single particle like a scalar with generic interactions. That could go through 3 to 2 annihilations. This could freeze out and produce the observed abundance. This is an old idea. kind of nowadays called Cannibalism by Carlson, Mahatchak and Hall, 1992. Where it could just have a different temperature. Actually, recently there's been kind of confusion developed where people have called this model excluded, but it was never excluded. That's still a perfectly viable model as long as it starts with a colder temperature than us by order 1 factor. So even just a single massive degree of freedom with generic interactions could, if it independently reheated, it could then freeze out and produce the observed abundance, and maybe we only couple through the reheating dynamics, which could be very suppressed. If it independently reheats, generically the temperature will be different. Like if it's not in kinetic equilibrium with us, it'll have a different temperature, and then it's either hotter or colder. So yeah, certainly that's not tuned. 50-50. Well, yeah, that coupling could be present if it's sort of natural if it starts small to stay small, say. But yeah, but indeed. Yeah, this type of interaction could be present. So in the nightmare case, I mean, assume it's not present, but if it is present, then you're good. You could have if different sectors are decoupled, then they stay decoupled under renormalization groups, so you can think of it as technically natural for the portal couplings to be small. But if your view is that all couplings that are allowed should be present with large couplings, then this indeed could couple through the portal, and then you're good. Okay. So I just wanted to enumerate nightmares just to kind of make the point that there's no guarantee we're going to get lucky. But even in these kind of nightmare cases, you can still have signals just due to gravity, like warm dark matter, fuzzy dark matter. So it can have self-interactions, which it would in here, which you could probe from galaxies. You could have substructure in our halo, which probes sort of the initial condition of dark matter. So there could still be a lot of information that we can infer gravitationally beyond what we know now that can teach us about the dynamics, even if we only couple it gravitationally. So the nightmare might not be too bad.
Because phi is only interacted with gravity and nothing else, then you say, it's like Lansdiki or whatever. No, some scalar associated with gravity, because if it doesn't interact with anything else.
I agree, yeah. But gravity kind of rich dynamics that we can study. Okay, good. So my plan after this depressing part is to kind of categorize different ways dark matter could be produced, just to give you some sort of overview of the landscape of ideas. So I'm going to start with thermal models, where dark matter, like the WIMP and its kind of cousins. And in the last sort of decade, there's been a lot of exploration of beyond WIMP variations. So I kind of give you some picture of that. And then I'll discuss non-thermal models, where dark matter is not in equilibrium, and that'll be after lunch, if you're still with me. So first, let's talk about thermal models. So this is the plan for the thermal part. So I finished my warm-up. So I'm going to begin with kind of a quick, what will be for most of you, review. So this would definitely be in the TASI part before we get to the gap, just to kind of set the language. I'm going to give you a quick review of thermodynamics in the FRW metric that will be needed to understand thermal models, and then we'll use those results to explore different models. But since this is kind of review that you've probably seen before, I'll go quickly through this next part. Like, what are the ingredients we'll need to review the WIMP and then study its extensions? Yeah, and kind of what else I hear, like, you can get, for example, from like Holben-Turner, chapter 3. I still find that reference really useful despite being old. Okay, so we'll be talking about models that are in equilibrium. So it's important to distinguish between the different types of equilibrium. So there's kinetic equilibrium, and then there's chemical equilibrium. So sometimes when people say thermal equilibrium, they mean a combination of these two, or so I don't really like that phrase, so I try to make a distinction always between kinetic and chemical. So kinetic means rapid energy transfer, which brings things into the equilibrium distribution. So like, for example, if dark matter, say, scatters against electrons, and if it exchanges energy rapidly compared to Hubble, then this will drive dark matter to have an equilibrium phase-space distribution, since the electron has an equilibrium phase-space distribution. So here, F chi will be given by the equilibrium distribution. Which in general has a chemical potential. And just as an aside, there are kind of some exotic models where you can kind of play with this and do interesting things with it. So I'll just say that as a okay. And then chemical equilibrium means rapid number changing. Right, like this process doesn't here time. This doesn't change the number, so only exchange energy. So rapid number changing would be things like annihilations, and just kind of schematically, if I have, say, 4 states, then if this is changing number fast compared to Hubble, then it sets the chemical potentials of the initial state equal to the chemical potential of the final state. So in general, you should consider all processes that can change number. That gives a system of equations for chemical potentials. In simple cases, it'll set them all to 0, actually. Like if you have, say, 3 to 2, and things can exchange, then you'll just set everything to 0. So during most of the cosmic evolution, the standard model chemical potentials are all 0. They can also encode, of course, asymmetries. Okay. Generically, chemical equilibrium implies kinetic equilibrium, but very importantly, not the other way around. Okay. Because if you can change number, you also are exchanging energy. So I'm not aware of any examples where you're in chemical and not kinetic, but the WIMP itself will typically depart from chemical equilibrium while it's still in kinetic equilibrium. So from that point of view, this is kind of a stronger condition. Okay. So it'll be important for thermal relic models to know the behavior of equilibrium distributions. And we'll be interested in number density, because we'll want to match that to the observed. So that's just given by the integral of the phase-space distribution, which you can sort of numerically treat in general. But let me just tell you the simplifying limits. So if high temperature, what we call relativistic, and just write a little table here, boson, fermion. Right, these are going to be different because of that. Okay. So we have this zeta function. And then this is 3/4 and boson. And then if it's non-relativistic, it's just given by the Boltzmann distribution. So yeah, the important thing to kind of memorize here is just that if it's relativistic, the number density goes like t cubed, and if it's non-relativistic, it goes like e to the minus m over t. We're not going to really care about the order 1 numbers in front, so I just wrote them here for fun. And then the other thing we'll care about is the energy density you just multiply by energy. So if I kind of repeat this table, then if it's relativistic, then you get this famous 7/8 here. And if it's non-relativistic, it's just m times this number density. Okay. Good? It'll be useful to know the total radiation energy density. Sort of everything I'll talk about, we'll consider dark matter production during radiation domination. You can also consider models where you make it during some early matter-dominated phase, which is interesting to consider, but for these lectures, we'll focus on the radiation-dominated era. Okay. Where G star sums over all the different thermalized states, which you can kind of approximate as a step function, because when things are non-relativistic, they're exponentially suppressed. So you just want to count the relativistic states weighted by their temperatures to the fourth, if you allow for different temperatures. Yeah, so this, for example, equals 106.75 when the entire standard model is thermalized. So when temperature is above m top, it equals 3 point something when the electron is non-relativistic. Okay. Okay, quickly telling you other things you know. I'll be just working in flat FRW. Which depends on the scale factor. We'll be interested in Hubble, because when I said things are in equilibrium or not, I always mean fast or slow compared to this. Now, during radiation domination, this, by the Friedmann equation, is given by the following, where then you can plug in this expression here. And then if you evaluate the order 1 numbers, we get the following. So Hubble goes like temperature squared over Planck. That'll be really useful to remember when we compare different rates to Hubble. And the other thing we'll need is entropy density. Here I'll just give you the expression. But it goes like the number of degrees of freedom times temperature cubed, which you could guess by dimensional analysis. This G star S is the same as this G star, replacing these 4s with 3s. So this counts the number of relativistic degrees of freedom. In equilibrium, the entropy in a Coulombic volume is conserved, and that means the entropy density tracks Coulombic volume. So, which is what makes this a really useful concept. So this goes like the scale factor to the -3. So we'll sort of always be using that to track volume. It's useful to define co-moving number densities, which are often called Y, because they can also be called yield, like your model produces the following yield of dark matter. So for a given species, this is defined to be the number density per entropy density. And this is a useful concept because if a species is inert, if it has no particle interactions, then this is conserved because the density is only changing with the expansion of the universe. So if you consider like a WIMP model after freeze out, this will be conserved, and then you can just map it to match the observed one today. So this is conserved for inert particle. Okay. final thing for this quick review is just to comment on how much dark matter we observe. This is what we want our models to match. And kind of, well, my favorite way of thinking about this is that the observed temperature of matter radiation equality we can think of as an observation of the amount of dark matter. Or this is when the energy density of matter is equal to the energy density of radiation. This is the energy density of dark matter plus the energy density of baryons. Which I can write like this. Okay, and temperature of matter radiation equality. Right, so we just want to set this equal to the radiation, total radiation density, and solve for temperature. And then we got some order 1 number that I'll call C times the dark matter mass times the dark matter yield. This is about 0.8 electron volts. This equality you can figure out from this expression, but this is about 1.8. So if we're kind of doing, I'm going to mainly do back of the envelope estimates. So the kind of useful thing to remember is that the dark matter mass times its yield should be about 1 eV, or about the temperature of matter radiation equality. So kind of useful to remember. That M dark matter times the yield after it becomes inert should be about T equality, or precisely about 0.4 eV, but about half of T equality. Or another way of saying the same thing is that omega dark matter H squared, which is order 1, it's 0.12, but then for a given model, or this would be, or let me be agnostic about whether it's the dark matter for some species. Its contribution to the energy density is its mass times its yield divided by T equality times order 1 numbers. So here I'm dropping order 1 numbers, but they're about, those numbers are about 2. Okay. So any questions with this quick review? So I'm going to now apply this to kind of review for you the wimp miracle, and then that'll be kind of a basic, that'll set a point of comparison to kind of more recent exotic freeze-up models that I'll highlight. Okay, so that finishes this. Okay, so here, yeah, by wimp miracle, I really just mean a thermal relic that's annihilating in the early universe through 2-to-2 annihilations. But I'll be agnostic about what the actual interaction is in the particles. So in the traditional model, this would be the weak interactions and standard model particles. But more generally, these could be beyond the standard model. I'm going to assume here that the dark matter temperature is the photon temperature. So which would, if this is a standard model particle, be just a consequence of this interaction. I'm going to assume that. I'm going to assume that this state is in equilibrium with 0 chemical potential. Which again would be the case if it's a standard model particle. Okay. So if you do things carefully, you can solve the Boltzmann equation, which can be written as an equation for the phase space distribution function of dark matter. Which is the following equation. This is called the collision operator. It's just you take the matrix element squared, you integrate over the phase space of everything in the initial state weighted by their distribution functions, and then the phase space of everything in the final state. But in practice, if this is in kinetic equilibrium, which is in traditional wimp models, then you know that this function is the equilibrium distribution function. You don't need to solve for its phase space, and then you can just talk about its total number density. So this I'll call an integrated Boltzmann equation, but people often just say Boltzmann equation for an equation for just the number density, which is just taking kind of one moment of the general phase space distribution function, which we can write like this. Where we have this collision operator that we've now integrated over Lorentz invariant phase space of the dark matter. Okay. And then, okay, for the specific case of 2 to 2 annihilations, this right-hand side, let me write this up here. It takes the following form. So this describes annihilations, and then there's a term for the inverse process. So here, my subscript will label the initial state. So these terms come just from this integral of the collision operator. And these are thermally averaged cross-sections, which just means this integral of the collision operator. Thermally averaged cross-sections respect the principle of detailed balance. It's actually a really useful concept in many different models, also in exotic models, but it tells you that the thermal average of a process weighted by equilibrium number densities is given by the thermal average of the reverse process. So you can solve this equation for this and plug that in back here. So this is normally what's done to write this in the following form. Okay. And then you can just use this equation. You can solve this numerically, which isn't too hard to do. There's a lot of public codes that solve this equation. Micromegas is an example that I've used personally. There's a bunch of other ones, like Dark Suzy. There's one public code I'm aware of that solves this equation. This is much harder. There's a code called Drake. I'll give you an archive number for this. And this is kind of only needed in exotic models where you're not in kinetic equilibrium at the moment of freeze out. And they do that by discretizing the phase space distribution and then solving a system of equations for the different modes. That's much harder. That only works for kind of specific examples. So I think extending that would actually be really interesting. But yeah, and this is done by many different codes. Okay. What the solution looks like. So it's kind of, to have time go from left to right, it's kind of conventional to plot inverse temperature. So define a dimensionless variable x should be the mass of the dark matter per temperature. It's nice to put the yield on the y-axis because that's the thing that's constant when interactions stop. If it were in equilibrium, this would just fall exponentially, the Boltzmann distribution. We can put 1 there. And what the solution will do is it starts in equilibrium, and then it kind of will look like that. This moment is called freeze out. And this, as you can kind of convince yourself by dimensional analysis and inspecting this equation, happens when the rate is about Hubble. So what people will sometimes, or at least what I would call a sudden freeze-out approximation, is you can just solve this equation and then set the late time yield equal to the number density per entropy at the moment this is satisfied. So, and that's a useful way of kind of quickly assessing the different models. So I'm going to use sudden freeze-out approximation. I'll review that here, and then I'll use that to describe more exotic models in a moment.
That code you mentioned, you can use it to get the distribution exclusion model, since it solves the unintegrated.
This Drake, I think, is designed for freeze-out, so it does 2-to-2 annihilations. There are kind of some special models that are resonant, close to a resonance, where you actually have simultaneous chemical kinetic decoupling. People have done that, but I'm not aware of a public code that does that. Yeah. Indeed. Okay. Yeah, I think more codes that treat this equation for more diverse models is really needed, in my opinion. So if anybody wants to work on that, let me know. Okay, so sudden freeze-out approximation, which gets things right within a factor of 2 to doing it carefully. So we call this will give me the number density at freeze-out, and then the late time yield. So, but the sudden approximation is to set the late time yield equal to the yield at the moment that this equation is satisfied, which then I can solve this for n. Okay. And now, so now I'm just going to do back of the envelope, neglecting all order 1 factors. Then the entropy goes as temperature cubed. Hubble. Here I'm neglecting the G star, the square root of G star. So the dimensional quantities are T squared over M Planck. This all happens on the order of the dark matter mass. Really, you say the dark matter mass divided by 10 to 20. But if I'm neglecting even that factor, then plugging all this in here, then the yield looks like this. And I told you, in general, the energy density is the mass times the yield over T equality. Plugging in this yield, then we have T equality and Planck. Cross section, this should be order 1, which means that the cross section should go like 1 over T equality and Planck. So this statement is what's called the Wimp miracle, because this turns out to be near the weak scale. Yeah, it ends up being like 1 over 20 TeV squared if you keep track of the order 1 numbers. But it's this geometric mean of temperature matter radiation equality, which is just an observation of how much dark matter we observe in our cosmology, and then Planck that enters from Hubble because of this rate comparison that sets the freeze-out moment. So those are the 2 scales, and those enter the cross-section that you need. Okay. But yeah, so let me just say more carefully. 1 over 20 TeV squared if you plug any different order 1 numbers there. Or like it's common to write, astronomers like, for some reason, units like centimeters in seconds, so they write that. Okay. Okay. And of course, there are still motivated viable WIMPs, like we heard about from yesterday, like the Higgs-Eno and the Wino. So those all kind of would respect this general parametrics. Okay. Okay. So this, I'm sure, was review for most of you. Any questions before I now want to talk about models beyond the WIMP and kind of give a kind of quick classification of thermal relic models and different recent ideas. Yeah.
With all of your own personal biases, how much of a miracle do you think the miracle is? Like if you had to quantify it, is it like a 1 in 10, 1 in 100? Like,
if I had to quantify it, it's $1 billion miracle in terms of experiments that's motivated.
$1 billion as in a billion, negative $1 billion that it costs $1 billion to do it?
Yeah. The sign would be negative. Yeah.
Historical sociological question.
You should go for more than that.
Okay, so of course, the WIMP miracle, for many of us who grew up with the WIMP miracle, it expanded at the time to take all the space in the room. But of course, there was compelling evidence for dark matter before the WIMP miracle took hold as a paradigm. What paradigms took hold before the WIMP miracle? Like what, if I were someone interested in models for dark matter before the WIMP miracle took all the air in the room, what would I have said was the deeply compelling explanation for dark matter?
I think people appreciate WIMP miracle does coincide with when people like.
There was no
Yeah, massive. Thank you, massive neutrino. There was I think more diversification in the early 90s before say LEP1. I think that was like when people like Lawrence Hall were thinking about 3 to 2, for example. So I think there was it was a little like right around in the 80s and around 90 it was a bit broader, and then I think it actually shrunk post LEP, because after LEP1 it was clear that we knew what everything was. Right? Okay.
Tony's point about nightmare scenarios not explaining the coincidence problem, those true for the WIMP miracle as well.
Yeah, from the WIMP miracle perspective, this 5 is a total accident, and also from Axion, all the proposed models for Axion abundance, it's also a total accident. Okay, so for the rest of this first lecture, I want to talk now about thermal relic zoology, and then I'll talk about non-thermal models later. So before I specialize to symmetric relics, let me pay homage to asymmetric dark matter, which is still a thermal relic with chemical potential. It's thermal in the sense that you normally use thermal processes to remove the symmetric component. The dark matter and anti-dark matter annihilate. That's a thermal process. Yeah, here's it's an old idea, but it kind of became generalized and named in its kind of modern form here. And the idea is you have some asymmetry that could be generated by sort of any of the ideas for baryogenesis applied to dark matter. And now the anti-dark matter all goes away. So that'd be kind of bar. And then you're just left with the excess number of dark matters, assuming an asymmetry. And this is like one potential way of addressing the fact that this is order 1 would be if there's some sort of relationship between the dynamics that sets the two asymmetries. Right, so we have the following, and this should be about 5. It's easy to make this ratio order 1. For example, you could have an operator that transfers an asymmetry between the two sectors, and then they're just related generally by an order 1 number set by chemical potentials. It's hard to make this number order 1 because then you need to tie the dark matter mass to the proton mass. So models that succeed in doing that would have like a Z2 parity and have dark matter be like a dark proton or dark neutron. The hard thing is the parity has to be good enough to preserve the mass under a normalization group, but not so good to have a huge amount of dark radiation, which you would expect if it looked like our sector. So models that succeed in explaining this, I think, are super interesting, but in practice get quite ugly in the details. No offense, Anson. Okay. But yeah, you can do dark phase transition, out equilibrium decay. You could baryogenesis could come from a dark genesis transferred or vice versa. So there's many rich set of possible ways of realizing this. And if you don't try to explain the 5, and in fact, then you could consider the case where this is very different from 1, and this is very different from 1, and that those. So and indeed, there are successful versions of asymmetric dark matter with dark matter mass to be anywhere between a keV and hundreds of TeV. If you don't try to explain the 5. Okay, so I'm going to now only talk about symmetric thermal relics. So let me put aside asymmetric. So let's assume no asymmetry, like is assumed for the WIMP. All symmetric thermal relics are kind of described by the same plot I drew for the WIMP, that you start in equilibrium, some freeze out event occurs, and then you're constant. The question that varies the models is what interaction triggers this decoupling. And the kind of generic approach is take your model, identify all processes that change the number of dark matter particles. The final one of those to decouple is the one that will set the chemical decoupling. And the earlier ones that decouple, we don't care. So identify the final process that changes dark matter number, and then you can just choose the rate such that that happens. So this matches the observed energy density, which means this has to be around 10 to 30, depending on the dark matter mass. Okay, so I'll just kind of get, this is incomplete, but I'll give a kind of list. There's what people call secluded, which really just be WIMP, but where there's no standard model particle or interaction strength. There's forbidden, where you're annihilating something heavier. So both of these would be the same diagram. There's famously co-annihilations, where you allow for multiple states here. Co-scattering, which we call something where there's, say, a scattering into a state that shares the dark matter parity, or I could call this something like that. Semi-annihilations. Where you have dark matter in the initial state and the final state. SIMP. Where you have 3 to 2. There's also successful models with 4 to 2, but those require the temperature to be colder than the standard model. I'm not aware of higher than 4 working. Maybe it could. But yes, say n to 2. So what each of these have in common are these are different processes that change dark matter number. The same, in general, the same Lagrangian will maybe have different processes, and then you can think of these different mechanisms as different phases within the same model, and you can indeed write kind of draw phase diagrams in certain models where depending on parameters, you'll be in these different regimes. And so here the kind of name is referring to the final process that triggers the chemical decoupling. Okay. So in the remaining time, I'll just discuss these in a little more detail. I might not have time to hit all 6, but we'll see. I'll just try. Yeah?
Are you going to get to self-interacting dark matter
Yeah, well, you could, some of these are compatible with large self-interactions. Yeah, no, yes, no, maybe, yes, no, yeah.
So I guess I was just wondering, in terms of, because you've been talking a lot, for lack of a better word, I'm going to use paradigm, in terms of paradigms, wimps, thermal relics do. How, from your perspective, should people be thinking about where self-interacting dark matter fits in? Is it kind of a broader class that has some of these qualities depending on which model?
Yeah, that's right. It's a broader class. It depends now on the model. But you could ask, like, could the same interaction type that triggers the chemical decoupling itself be a measurable self-interaction? The answer is no for WIMPs, because the weak scale because observable self-interactions need nuclear scale cross-sections, which are much smaller than weak scale. But actually, some of these mechanisms do point to interactions that can be nuclear sized. So some of these are compatible with the freeze-out being related to self-interactions. That's true for forbidden and SIM. It's not true for WIMPs. Actually, it's model dependent. So some of these are compatible with self-interactions and some are not. And then sort of to any model, you can then add additional interactions that give observable self-interactions. So it's compatible with any of these, but if you ask, could it be related to this, then yes for some and no for others. Yeah.
And in some of these scenarios, there's a subtlety having to do with kinetic freeze-out.
Sorry?
In some of these, there's a subtlety related to kinetic.
Yeah, the subtlety can be, in some, as far as I'm aware, always chemical equilibrium implies kinetic, and typically in these thermal relic models, you're still in kinetic equilibrium at this decoupling, and then things are simple. But in some models, you can have simultaneous chemical kinetic decoupling, and then that becomes more complicated.
Of these scenarios, which ones of these do I have to think carefully about kinetic decoupling? Like SIM is one where I have to worry that there's a process that keep me in kinetic equilibrium to make sure that I don't.
Well, yeah, even for WIMP, you need to work, for any of them, you need an additional process, otherwise it's simultaneous decoupling. So if
I don't like simultaneous kinetic decoupling.
Yeah. So
I need to have kinetic decoupling later.
Right, and then any of the models need an additional interaction. So you need to be careful for any of them. If the
Not the ones that I write on the board either.
Right. So
all of them you can
yeah. If the interaction that leads to chemical decoupling is the only interaction, then you will have simultaneous chemical and kinetic decoupling, and in general, you will distort the phase space distribution at the moment of freeze-out. And that's been treated explicitly in WIMP-like models in that Drake code, and we considered it in examples here. But basically, for any of these models, you should add an interaction that maintains kinetic equilibrium. But that'll kind of generically happen in WIMP models because you can rotate the diagram.
Sure, so the ASI factor is some of these have crossing symmetry that makes me not worry about it. And then the ones that don't have crossing symmetry, is SIM the only one that I don't worry about? Or that I have to really worry carefully because of generically crossing symmetry, or other ones I have to worry about?
Okay, let me think. Yeah, for I would say you should also, you also have to worry for the co-scattering, and yeah, you should kind of worry for all of them, honestly. Because even, for this sort of I think you can come up with examples for all of them. So always worry?
Always.
If you just say crossing, it just means the other one is of the same size, the number not changing.
Yeah, so.
You may need some kinematic enhancement for that number to be bigger than the amount.
Yeah, exactly. Yeah, so the reason why crossing usually maintains kinetic, just to say, is at freeze-out, these are non-relativistic and exponentially not abundant, and then when you cross it, therefore, yeah, it's really abundant. So when you cross it, now, assuming this is relativistic, then this is exponentially more abundant than the crossed one, and then that's the usual argument, and that breaks down if this state is massive compared to that one, which can be the case in some of these. So okay. Yeah, I think we can kind of case by case discuss it. It's hard to make general statements for me. Okay. I don't have much time. I think I might not have time to do all 6. Are there any favorites? or I'll just kind of quickly, I could also continue this part of the lecture after lunch. I refuse to do that. But I'll just kind of go quickly. So by secluded, I really mean the same thing as WIMP, but just making the explicit assumption this is not a standard model particle, and then therefore this interaction can be totally different than standard model couplings, but still it should be the same parametrics that I described. But if I now call this, say, alpha dark, for the WIMP, so let me just say this would be kind of some weak coupling like alpha 1, alpha 2. And then if we solve for the dark matter mass, this is sort of some weak coupling times T equality and Planck. That works great because this is tens of TeV. This brings this down to TeV. But now if we allow this to be much smaller, then we can make this weakly enough coupled that we can go all the way down to KeV. Then you run into warm dark matter balance. So this model doesn't work lighter than 1 KeV. Or you can take this to be strongly coupled, and then that's called unitarity bound, and then the maximum mass would be a few hundred TeV when it's just strongly coupled states annihilating. So by secluded, I mean just be agnostic about this interaction strength, and then the mass, the possible mass extends all the way from KeV to hundreds of TeV. But and this is not something you can test in with self interactions because this is weak scale. But the mass can vary. Yeah.
Where do the main warm dark matter bands
come from? For example, Lyman alpha forest but yeah, so it gives if dark matter is too light, you get a
structure on short scales.
Exactly.
Forest gives you the best indications.
Yeah, or one indication. Yeah, and then there's also you can affect the population of dwarf galaxies. Would be another example. But yeah, so really, then the matter power spectrum has a cutoff. That's, but yeah, you're exactly. The intuition is you're removing structure on small scales. So that ends these models at about a KeV. The models that survive that are lighter need all the dark matter to have zero momentum, which is not true in models where you begin with a thermal distribution. Okay, so forbidden is the idea that you can contemplate the same process, but allow this to be heavier than this. And now you do need to be worried, Jesse, about kinetic equilibrium, because now the rotation no longer implies this is no longer exponentially more abundant. But still, this should be 1 over T equality and Planck. If you're annihilating something heavier, that's not allowed, of course, if the two dark matter are at rest, because it would violate conservation of energy, when in reality the thermal distribution, so you can use the tail of the distribution to access heavier states. And then this parametrics doesn't work anymore. This really implicitly was assuming you can do it at rest. So now you have to be careful about the thermal average, but a trick is you can use detailed balance and then write this cross-section in terms of the reverse. Yes, and again, here I mean, okay, it's less than phi. So the reverse process is allowed with the phi at rest. So detailed balance here. Tells me the following. This will be just of order alpha squared over m chi squared rather than pi squared, but they have to be similar here. And now I can solve for this. And then these ratio of equilibrium number densities just gives me an exponential from the Boltzmann factor. So this cross-section will go as e to the minus 2m over temperature alpha squared over m chi squared here, neglecting order 1 numbers. Sorry, that's a 2. That's important. Shouldn't neglect order 1 numbers in exponents. We're here defining delta m 2b m phi minus m chi. So this is just telling you that only this fraction of the thermal tail, of the high energy tail, has enough energy to access this heavier state. And now this should go like 1 over T equality m Planck, which if I now solve for the mass, I get this exponential. So what this allows is for the mass to be smaller than a weak scale, even if the alpha is strongly coupled. So you could even have like composite states in some light sector. And so now the mass, whereas in the secluded case, to get the mass light, you need to become very, very weakly coupled. So you kind of need to suppress to get light masses, you need to suppress the annihilation somehow. Here you can suppress it with a very weak coupling. Here you're suppressing it just with the thermal distribution. So you can now be exponentially lighter. This now the self interactions will be of order alpha squared over m squared, and those can now be observable because this exponential sets a hierarchy between the self interactions and the annihilations. So this is compatible with large self interactions. Okay. Let's see. I want to keep my list, so I'm going to erase from here. Yeah, so this is the most famous in this list. So this is actually treated in all the codes like Micromegas just do this sort of automatically. And it's just a statement that there could be multiple states. So we can kind of number them that are all charged under the Z2 parity. So like of course in SUSY, this would be the list of sparticles. And now they're all annihilating. So you should in general consider their mutual annihilations. But at late times, they'll all decay down to the lightest state, like the neutralino say. So here, but the heavier states, like even squarks and gluinos, in the SUSY case, are participating in annihilations that can affect the chemical decoupling. In general, you need now, if this goes up to n, you need n different coupled Boltzmann equations, which is annoying. But if you assume that these different states in the tower are in chemical equilibrium with each other, that gives you n minus 1 constraints, and then you can write just one Boltzmann equation for their overall number density, which takes the same form as the WIMP equation. Where you define the total number density to be n, and this effective cross-section that enters, which should now be weak scale, is a sum over sort of all possible annihilations weighted by their number densities. And this whole sum should be weak scale. But now you could have cases where there's only one dark matter initial state, or even more interestingly, the sum can be dominated by annihilations with no dark matter in the initial state. That actually happens in SUSY examples called Bino-Wino co-annihilation. Only the Wino annihilations actually set the chemical decoupling, or things like squark, Bino, only the squark. So the dark matter might not even be in the initial state of the process that sets the decoupling. The only requirement is it's in kinetic equilibrium, which is a much weaker requirement, which completely can divorce the interaction that sets the dark matter abundance with the interactions that you would be able to test experimentally. And you can actually, in general, have exponentially smaller direct detection, indirect detection than in the WIMP model where there's only one state. So it seems like a boring complication, but actually, from the experimentalist point of view, this is an exponentially important effect to consider when you have multiple states. And dark matter doesn't need to be in the initial state, and then the abundance of dark matter is now independent of its couplings parametrically with the assumptions in kinetic equilibrium. Okay? Yeah, so co-scattering, you can think of as a different phase of co-annihilations where you relax the assumption that the different states are in kinetic equilibrium, and if the exchange processes decouple before the annihilations, then you can enter sort of a different phase. So let me call chi the dark matter. And here, this is, in terms of the Z2, this is Z2 odd and even. This is what this notation represents. So this is some state that is assumed itself to be in chemical equilibrium, like from, say, very large annihilations. But take this to be heavier than this, but in chemical equilibrium. Then, so then co-annihilations would mean that this process decouples before this. And so co-scattering is where this process decouples before that. So there are two different phases of the same model. But if this is the first thing to decouple, then the dark matter abundance, instead of being set by annihilation, is set by an inelastic upscatter. Here, the Boltzmann equation for this. So in the limit where this is in equilibrium when this decouples, then we can just write a Boltzmann equation for this process. So after using the detailed balance trick, we can write the following. Freeze out is now when this is satisfied. And then, so now notice the freeze out depends not on the number density of dark matter, but on the number density of another state from the bath, which could be lighter, and then you can have an exponentially smaller cross-section at the freeze-out moment. So this is so now if you kind of go through the same argument, the fact that this is exponentially different than the number density implies that the cross-section should be different by the following exponential factor. So if this is lighter than this, then now the cross-section can actually be exponentially smaller than the weak scale rate, which is, say, exponentially important for things like direct detection. So you can have sort of ultra-weakly coupled dark matter where the interaction rate is much smaller. Okay.
Like a nightmare too, but only milder.
Yeah, milder. Only, milder. Maybe a weird dream, say. Okay. Okay. Semi-annihilations. Which are Jesse's fault. Would be you have dark matter also in the final state. This is compatible now with, say, a Z3 if that's the antiparticle, where these two have the same charge as the antiparticle now. So instead of a Z2, if you have a Z3, you can consider this. The Boltzmann equation, if you use the detailed balance, it has a slightly different form. But you only notice if you squint. The difference is one of these, for the WIMP, these are both equilibrium. Now one is not. That doesn't matter in the limit of sudden freeze out. So still, this should be weak scale. It only gives an order 1 difference compared to the WIMP Boltzmann equation. The key point here, of course, is that a crossing of the diagram no longer guarantees direct detection. So unlike the WIMP, but you can still have indirect detection if this is a Standard Model state or decaying to Standard Model states. But you do still need a WIMP-like cross-section, so that's still preserving, say, the WIMP miracle. Okay, and finally, SIMP. Which is an acronym for strongly interacting massive particle. Although it has nothing to do with the strong interactions, and the interactions don't need to be strong. So personally, I'm not a fan of their name. But the idea is to consider 3 to 2 annihilations. If this is the only process in the model, then the model undergoes a weird thermodynamics called cannibalism, which basically it only loses energy logarithmically with the scale factor because it needs to preserve entropy. But if you add to this some other interaction that maintains kinetic equilibrium with the thermal bath, then it's more, say, WIMP-like, and that's the limit studied here, is to add this type of interaction. If you only have this, then it needs to have a colder temperature than us to not be too warm. And that's the old Lawrence Hall et al. 90s version. If you add both of these, then that's this modern version. Here, the Boltzmann equation, after using detailed balance, for 3 to 2, it turns out there's a v squared. And by the way, if you don't want to learn how to compute thermal average of 3 to 2 processes, you can use detailed balance and then describe it in terms of a thermal average of a two particles initial state, which is easy and can be done with public codes. So that's just a tip here. But anyway, here the freeze out condition has an extra number density in initial state. Which changes now the scaling with regards to the Hubble parameter and the cross-section. And now if you go through, but now this you can plug in, so as usual, the energy density is mass times yield, which is number density per entropy, T equality. Now plug this, sorry, there's a 1/2 here. Plug this in here, and now ask what size the cross-section should have. And now it actually depends on the mass. The mass doesn't drop out like for the WIMP. The 3 to 2 cross-section has mass dimension 1 over mass to the 5th. And now if you plug that into here, and ask this to be order 1, yeah, so this will say go like some alpha over mass to the 5th by dimensions, solving for mass. You get the following sort of generalized geometric mean of T equality and M Planck. You can generalize this to n particles initial state, and then you just get higher and higher powers of T equality appearing in the mean there. But this now, whereas the geometric mean T equality on Planck is tens of TeV, this factor is around GeV. So that's why they call it strongly interacting. If alpha dark is 4 pi, then this should sort of be similar to QCD strength interactions. But alpha, this can, just like WIMP, this can be weakly coupled, so you can take alpha dark to be small, so there's no need for it to be strongly coupled. Really, this statement is just instead of weak scale, it's a strong scale cross-section. That's compatible with large self-interaction strengths if the alpha dark is 4 pi. So this and the forbidden are both ways to have alpha dark of 4 pi, keeping states light enough so that self-interactions can probe the process, the scale of the process that leads to the chemical decoupling. So final, I'm out of time. Let me just kind of, in 1 minute, kind of give a schematic phase diagram to put some, kind of unify some of these ideas. So let me take dark matter mass here. And by alpha dark, I mean schematically the coupling strength that describes the dark matter's coupling in the process that leads to its chemical decoupling. Now let's consider a wide range of masses. Say hundreds to the yeah, so this is say 4 pi. Then unitarity is just a statement that couplings can be at most 4 pi. Warm bounds would be sort of over here. Two to two models would be sort of secluded would be a line that ends at around 10 to the minus 11. Or like traditional WIMPs would be here. And then secluded, what I call secluded would be this line. The 3 to 2 by this numerology leads to a different line. Where the kind of strongly coupled version that they call simp would be there. Yeah, that's ending now at 10 to the minus 6. And then the forbidden model, yeah, so along this line, M chi goes as alpha dark to equality and Planck. Forbidden models would live above this line. Because of that exponential. Yeah. And, well, the kind of co-scattering can actually be down here because of the fact you can be scattering against an exponentially more abundant lighter state. So co-scattering, depending on whether the state you're co-scattering with is lighter or heavier than the dark matter, can actually be above or below, but those would live in the lower part. Well, let's just kind of highlight the below part. Co-annihilations in general will live below the line. If we call alpha dark the strength of the chi-1's interactions, because you could be dominated by the heavier states. So sort of WIMP is there, vanilla 2 to 2 there, 3 to 2 there, and then forbidden would move above, co-scattering co-annihilations below. Okay. So it's lunchtime. So all of that are thermal relic models. They all have in common the assumption that dark matter began in thermal equilibrium, which makes them theoretical close relatives of the WIMP. If you can stomach more of this, after lunch, I'll talk about non-thermal models, where dark matter is never in thermal equilibrium, and that points to different dynamics and different couplings, strengths, which is very different from the experimental point of view.
Someone have any residual questions before we're done? I'm going to pose a question for you. It's probably best answered at the end of the second lecture. But in the interest of bridge building, if I'm in the audience and I work on asymmetric bootstrap or amplitudes or lattice QCD, what are the questions in the space of theories of dark matter that might be amenable to methods from other parts of the field? Do they all live in the hashed circles, between your asymptotic states? So that's maybe a question to answer at the end of the second lecture. But I just want to put it in that.
Yeah. Let's talk more later. But yeah, for now, at least if you're a model builder, then these are the different things to look for happening in your model. And you can identify models that exhibit these different behaviors. Computationally, if you're interested in that aspect, then things when you're departing from kinetic equilibrium and studying the full phase space distribution are interesting. Amplitudes, I have to think more. But in strongly coupled models, there's strong dynamics that can enter rates that are relevant here at the unitarity bounds. So that, of course, is interesting.